All right, so we have our waveforms here again. Actually, let me grab the power that we just calculated, and we'll throw that in here. And let me also just grab the circuit, because why not just have it with us just to stay consistent. Make it a little smaller. So that's the circuit we analyzed. We found the power. We also had VFT and IFT here. Might as well get those as well. And we can just put those right here. All right, and so we found this power, and now we're talking about the average power, or sometimes it's called the real power. You'll see why that's relevant later, but for now, let's just think of it as the average power. And what is it? It's just the average value of instantaneous power over one period. And so if we were to take the average value of this purple signal, we'd probably get something right around here. So I'll just sketch a little dotted line of the average power. And how do you compute that value? Well, just like we did previously, we just take the average value of the signal that we found, which is this power signal right here. Of course, this computation will change depending on the load. But for the purely, because I talked about previously that if there's a phase shift, then something else interesting happens. Nonetheless, if we compute this average the way that I'm about to do it, it will always work for any load. But in the next slide, I talk about a different way that we can compute the average power, which might be a little bit easier than all this time domain stuff. But for now, let's just do it in the time domain to show that it works, because I think it's useful. So we talked previously about the average value of a signal. So for this case, it would be P average. And we would say that it was 1 over T times the integral from 0 to T of P of T dt, which is great, and it works, and we used it. But again, I like the integrating over omega t a little bit better. So I'm going to write the alternative, which you probably could have guessed is 1 over 2 pi, 0 to 2 pi, P of omega t d omega t. And of course, because this function is a function of omega t, we are perfectly fine to carry out the math like that. And so I'm going to carry out the math like that because I think it's a little bit easier. So for us, let's do P average is going to be equal to 1 over 2 pi, integral 0 to 2 pi of my signal here, which is 50, times 1 minus the cosine of 2 omega t d omega t. Of course, I can pull a 50 out. That's going to become 25 over pi times the integral from 0 to 2 pi of 1 minus the cosine of 2 omega t dt, or sorry, d omega t. And then pretty easy to take these integrals. Let's go 25 over pi. The first integral is just omega t. The second integral is going to be minus a 1/2 that I have to pull out from the argument, the sine of 2 omega t. And then this whole entire expression is going to get evaluated from 0 to 2 pi. Okay, so we can do that pretty easily. So the first one is going to be omega t is 2 pi minus a 1/2 the sine of 2 times 2 pi, which is 4 pi. And then that whole thing minus omega t is now 0 minus a 1/2 the sine of 0. All right, so that is our expression for the average power. A lot of things here cancel or go to 0. Let's take a look. The sine of 0 is 0, so this term is 0. This is obviously 0. The sine of 2 pi, or the sine of n times 2 pi, or sine of 4 pi here is also 0, so this whole term also goes to 0. And all we're left with inside the square brackets is this 2 pi. Well, I can cancel this pi with this pi, and I am left with a value of 50. My units, of course, for my power were milliwatts, so my units, since I haven't messed with anything, are still milliwatts. And so my average power that I calculated is 50 milliwatts. And so that should make sense. In the previous case, when I calculated this signal, of course, there's going to be points in this signal where cosine reaches a maximum. And this will become 50 plus negative 50, or sorry, 50 plus 50. So I get a peak value at about 100 milliwatts. Not about, it's exactly 100 milliwatts. And so my average value of my sine wave, which should be half is right at the halfway point, which we just computed. It's 50 milliwatts. Okay, so that makes sense mathematically. And again, this will work. I wrote here for a purely resistive load. I maybe shouldn't have written that. I wrote that for the next slide because the next slide uses a different way of computing this average. And we're going to see that both of them are equally valid for resistive loads. This method that I've done here is valid for any load. If you have your power signal and it's not for a purely resistive load, and it actually starts to shift down into getting some negative values because of the phase shift, you can still take the average value just like this and it's going to work out. But in the next slide, I'm going to show you how to take the average power quite simply, which doesn't require all this integration. Actually, it might require just as much because we still have to find RMS values, but it's just an alternative way of finding the average power. I think it's useful to show all the different ways that you can do it, and then you can often choose which way you prefer to calculate whatever it is you're trying to calculate. But for now, we basically have our instantaneous power function, a function of t, which we know how to take the average value of a signal. I have two alternative versions of the equation here. One is taking the average value with the integral being respect to time. This is with respect to angles. I personally like this one better because the math works out pretty nice when you do the integral. Obviously, you see all these things very easily cancel because we're integrating over radians. And we get our average value to be 50 milliwatts, which from the signal that we have would be expected. Okay, so in the next video, I'm going to show you how to calculate the average power a different way, and we're going to arrive at this same value. Okay, we should arrive at 50 milliwatts doing it the other way. And of course, you can pick which way. The reason why the other one is useful is because a lot of times we already know a lot of the information we need to calculate it, and we can just avoid doing all these integrals. Okay, so I'm going to go ahead and end this video. And yeah, in the next video, we'll talk about an alternative way of finding the average power.